Hello friends, thanks for stopping by my channel. So today we'll be doing another system design, and the problem that we have today is called sales rank. So let me first write down the problem statement. So let's imagine an e-commerce website like Amazon. Um, so what they have different products that they will showcase on their homepage, and then the products will fall under some categories. For example, like you have electronics, and then under that you have laptops, phones, different kinds of mobile devices, tablets, etc. And then you have categories of home decoration. Under that you have sofas or flower vase, etc., etc. So what we want to do here is whenever a user logs in, um, whenever a user is logged in, the user is shown uh, top products per category. So let's actually understand this problem is like so one particular user will not be interested in all category of products. So we will only so we'll have some kind of mapping like what that user is basically interested in. So the user to categories mapping, and then along with that we'll have uh, per category what are the top products that are there. So given a user what are the categories that the user is interested in, and given a category what are the top products inside. So for example, if I log in and I mostly buy electronics, then I'll see electronics as a top category, and under that I'll see what are the top products that inside that. So how do we design a system like this? To start that, actually first let us put a timer here. So we'll put a timer of around 45 minutes, and then we'll have a buffer of 50 minutes, which is the standard duration for any interview. Let's start that now. And now let's try to understand this problem. So the first part of the problem is understanding the requirements fully. So let's write down the functional requirements. So the functional requirements here is ideally in our case, we are mostly interested in designing the service which helps to do that. So something that is out of scope, which is the UI component, like how in UI the data will be shown. And other thing that is also out of scope is the exact algorithm that we are using, the algorithm to find top content. So there are multiple algorithms that we can use. One nice algorithm is just based on the frequency. We can do that, or we can add some kind of sophistication techniques to find the content. So we can assume there might be some algorithm to find top category of products. What our service needs to handle is basically the volume of data that will be coming. So the requirement specification, when we are doing that, as part of that, we'll have the first requirement of the service is, let's think of it as an API, because it will interact maybe with the front end service or the web server, or whichever it calls it. So the API will have is um, get top categories, I would say, or you can say uh, something like get top products. That is better. So get top products given a user ID. What this returns is you will have it will return sort of like a map of category, and per category you have a list of products. So whenever we do that, we'll just say for this given user give me the number category and then the list of products. So that should be my API signature for this. And the other thing, I think that is the main requirement that we have to do for this. The other part that we have to do is storage and storage of now how would we do that? So to do that, actually we have to allow the ingestion of the data. So let's say let's say we have a separate algo to run on top of it. So we'll store the data. Uh, what are the data that we need to store? Store the transaction data. What do we mean by the transaction data? So the transaction data basically means, since we want for per category what are the top products under there, we want to find out for a given, whenever a transaction happens, what basically happened in the transaction, like what product got purchased, which category it falls into, how many items got purchased, what was the price in that. So all those data we need to find out and figure out more relevant information for the user. So we need to store the transaction data in a meaningful format such that we can convert it into API data. And so we'll come into that how but we come part of as part of the data model design. But that will be one requirement, that we need to store the transaction data in databases and retrieve this retrieve. So in a nutshell, I guess that is the requirement that we have. Now let's come to the other non-functional requirements. So non-functional requirements, since it's like a service design, there is not much non-functional requirement as part of it. So we'll jump into directly the capacity estimation part of it, like how much we need to store, what do we need to store, and what will be the bandwidth requirement, what's the typical latency that we're looking for, coming to those numbers. Before coming to those numbers, actually, let me first have a brief understanding of the data model, or what are the data that we need to store, so that we can have an estimation of that. So since we need to figure out, um, I think we don't need the user specific information, or we can assume like the user specific information will be available in some other database. So let me pick up some uh, common example databases like this one, and I'll sort of replicate this and place this. So this database, what this will contain is basically the transaction data. So one database, we need to hold the transaction data, and then from the transaction data, what will happen is we'll have the transaction data coming from side. So call it transactions, incoming transaction logs, right? So this will be our incoming transaction logs, and this will be stored in the transaction data here, this transaction DB, and we'll come to that how we'll store that in DB. And then we'll run different kind of algorithms on top of the transaction DB, and then there will be a final database which will store, we can call it the um, user uh, user preference DB, which contains the user preference. So there will be some job which will be running intermediate in between. So let's identify that job as um, so the exact detail of that I'll actually come to it. Resume for now have some ranking job. Simple, simple happening here. So let's call that uh, ranking job. So this ranking job will take a volume of transactions, and from that it will basically uh, compute the user preference DB, or populate the user preference DB. And Then the final request will be served from the user request. Connect this, this will be this, and let's actually assume this data block. Make it up. The main thing that we need to care about for the data estimation part is whatever we need to hold for transaction D. So because finally from that we will book some data. So for transaction, let's assume a schema. So first we are trying to do storages. So for transaction, what the data we need to store. We will have a product ID, and then we'll have a corresponding category ID, right? And corresponding to that, we'll have the user ID who is actually purchasing that, and then we'll have a total price, or let's say price, and then we'll have quantity, then we'll have some timestamp, is like some created time value. So I think these are the things that I can imagine for now, and should be sufficient to calculate the ranking job. So all of these IDs typically, and the volume of data in terms of transaction in Amazon, if we think about, so typically we'll have about total the number of transactions that we need to handle. It will be, let's say, 1 billion transactions per day. So we need to have 1 billion transactions per day, and then once we have that data, then it should be out here. That, and what we have here is uh, outgoing outgoing response. So, so this outgoing response will basically contain a format like as I mentioned here. So it will have a user ID and then a map of category ID of product. Structure sort of identifies how we want to store user preference. And so we have 1 billion transactions happening per day, and along with that, let's say in each transaction we have this product ID. So let's assume product ID we have 64 bits. So we have 8 byte of product ID. Um, let's all of them are in bytes. I'm not writing again and again. So we have 8 byte product ID, 8 byte of category ID, uh, 8 byte of user ID, and price is also, it's not bad actually, but we'll have say 4 bytes of price. Quantity is also same. Create that to be a little bit larger. So let's do say 12 bytes we have there. So in total, I want to come up with a round figure here. That becomes easier. So we have like 24, 28, 32, 42, 44. We have around 44 bytes. So, but it's, yeah, it's fine. So roughly we have around 50 bytes. Or let's say originally we have 60 bytes per transaction. Then if we want to save all of these transactions in databases, then this will sort of cost a lot. So we have 60 byte per transaction, then we have 1 billion transactions per day. Then the total volume of the data, the total storage, if we assume we are storing data for the last 5 years, or let's say 1 year, then we can compute that. Total storage per year for transactions would be something like you have 60 bytes of data, then you have one a lot of zeros, 1 billion transaction, per day, then you have 365 days. So these many bytes of data. If we divide them by, let's say, this is like KB, MB, DB. So we have 3, 6, 12, uh, 3, 6, 12. Let's move 1 0 from here. So we'll come up with around 21.9 or 22 terabytes of data, 22 terabytes of data per year, if you want to save that for the transactions. And then we have the user preference DB. So that won't be that large because the number of users, I mean, how much data we can potentially save there. So we have, let's say, 1 million transactions per day, right? So this is for the, let's say the number of users. Amazon has 500 million users. Of course, we don't need to save the data for all the users. So if, let's say, 70% of the users are active, so if 70% active users are there, then we need to save around for 350 million users. And the data would be in the same format, like we'll have a user ID. And then for a given user ID, if I just flatten it out, like I'm thinking of a JSON-like structure here for this output data. But if I flatten it out, we'll have a user ID, then a cat ID, and then a product ID after that. So this data set can be replicated like per user. We can save, let's say, on an average, we have 10 categories saved per user. And then for each categories, we have 10 products saved. And as we have seen, all of them take sort of, so which basically means we have total 100 entries on an average per user. So 100 entries into 24 bytes. It will not be too much compared to this 22 TB data. So we'll have 100 into 24 bytes of data. And this will be computed and refreshed at the same rate. So it won't be that much volume. So the key part would be challenge would be keeping this transaction. But yeah, I think coming back to the uh, bandwidth estimation part here, the bandwidth is will be sort of determined. So, and another part is like how many requests will be coming. So the request will be coming every time the user loads a page. So we have 1 billion transactions coming in per day. And let's say every transaction happens for 100 times the user opens a page. So you have 100 billion page views per day. Uh, in this case, what happens is like we have these many requests and 100 billion times we have the request coming into the user preference DB. And so the user preference DB, if we want to assume the what would be the typical nature of the service, the typical nature of the service will be read heavy because our read to write ratio is about 100 is to 1. And the way we are going to serve is like how much we need to serve within a second. Let's say we have 100 billion page views within a day. From here, actually, this is the heavier operation. So from here, we can actually do the capacity estimation for bandwidth. So we are sending the data in a format of like 100 entries of 24 bytes. So 2400 bytes for each user and 2400 bytes. And then this requests are coming for 100 billion page requests. So a billion is like a 9. So we can take that as 1 GB in that. But I think let's actually divide it. We have 100 billion. So it's like 10 zeros, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we do 100 billion divided by 365, not 3, 24 to divided by 60 by 60. So per second, we have these many 100 million uh, requests coming in. 100 million page views are basically translating to about these many page views or requests per second. So you should be able to handle, uh, let's think of an upper cap of that. So we have to handle 150,000 page views per second or 150,000 requests per second. And in each request, we are sending approximately 2,400 bytes of data. So we are sending 150,000 into 2,400, which is 1, 2, 3, 4, 5, 6, and 24 and 5 is 120 and 12 and 36. So how much is it? This. So we have around 360 million uh, Mbps. So that's the speed that we need to hit, 360 Mbps. And that is our bandwidth requirement. Like we should have that much bandwidth to serve this request or whatever is coming to DB. So now I think we have spent enough time on the storage estimation part. So let's come to the section for, and we have also designed a brief of the system. So what I'll do, I'll basically pull this section to this side here, maybe reorganize a bit, uh, organize a bit more on the side, right? And move this here. And then we have all of these sections which we want to move on this side. Okay. And now coming back to how we are going to save the data to the transaction DB, how the ranking job will come on its part. So we are trying to design the service. We are not trying to see how exactly the transaction logs are basically the transaction happening. So we'll start from somewhere. And since we are designing the service here, so we'll start the assumption like we'll have a web server where the actual requests are coming from the front end, and then we are logging the transaction log. So let me actually start drawing a set of servers here, which will basically, yeah, so can I edit them? No, can't. Browse, delete this stuff. Do I have any web server equivalent here? Something like this. Yeah. So I'll have sufficient number of web servers which are actually serving the request coming from the users. And what these web servers will do, they'll just forward this request. So two things. One thing is like they'll request our DB that we had created here, the user preference DB for this request. So actually, let's put this guy in here and bring these folks also down. Remove this for now. We have a ranking job, and then we have a transaction log. Incoming transaction is basically coming from the service here, point here, and right, and incoming transaction logs are here. Have the ranking job right here, and then the user preference DB will come. So what are the key challenges that we have in terms of it? So now let's come back, coming to the our DB flow. Incoming transaction log for this. The transaction DB, we The transaction DB will have a structure like this. Uh, as I mentioned, a schema like this: product ID, category ID, user ID, price features. So we can think of like a relational DB storage here. But the problem is for relational DB, it's very hard to scale. We can do multiple scaling options there. We can try out. Obviously, we have to have multiple replica for the same DB and distribute the incoming requests that are coming. Even if the request is quite large, even if it's not like 150,000 page views or 150,000 requests per second, it will be 1500 requests per second. So even 1500 requests per second should not go to one replica of the DB. So we should split it out into multiple DBs. So we can do some kind of option like sharding for the DB, and the sharding we can have. So what I can think of is like, since this data is essentially a very relational structure data, I want to keep a relational structure for this particular data set. So this is a relational DB that what I'm thinking of. So that's why I guess the color I should think of like this. We have something like this. And this is a sort of, I'm thinking of a document storage. It will color will be like this. The property of these DBs, let's talk about actually the transaction DB. So transaction DB, I'm thinking of it as the relational storage because the underlying data has a very consistent structure, and usually, since logging is a critical flow, there are very less chances of changing the flow of data that we want to put, uh, because that log is basically will be used for billing and revenue generation and a lot of stuff. So usually logs are very stable schema, and changing the schema will destabilize a lot of systems. And since we are consuming a very stable schema, we can have the transaction DB as relational storage. And if we keep that as relational storage, the challenge that we have to face is replication and sharding. So for sharding, we have to come up with a strategy of how to distribute the load across. So we have a product ID, category ID, and user ID. So these are the basically the user ID and the product ID. This is the key that's there, and one product ID will map to one category ID. So even the category we don't need to store here. So if we remove the category, we'll actually save some of the database space here. We can reduce say 10 bytes of space here. So approximately, so that will reduce like 1/6 of it. So 16% storage reduction will happen. So eventually, if we have say 22 and 0.84 of that, so it will come around not much, but something like 19 terabytes of data. And then we have the so now if we have the user ID and product ID as key. So for this data set, we have the user ID and product ID as the key, the composite key. We can do a hashing based on top of that. So this hashing where can lead us to one shard ID, but underneath we want to have as many scale. Uh, we don't want to map exactly the user ID and product ID to a physical shard. Instead, we want to do a logical shard. So the way I'm thinking here, we'll use consistent hashing to map these to a large number of logical shards, and individually the logical shards will map to some of the internal shards. So we can figure out like which database actually this data maps to. So I'm using the same idea for uh, but the problem is actually it's not built into the database itself. So if I mean in most of the relational storage, the concept of this scaling is not built into itself. So that's why the scaling becomes a challenge there. And the other scaling actually it's not very reasonable, like SQL tuning or a vertical scaling, just increasing the capacity of the database or uh, doing federation of that, because we can't do much federation here. We have a single data storage. So what we can think of is this transactional DB instead of a relational DB, since we have to do this partitioning scheme of that, um, we can have a kind of um, a document store. And the advantage of this is if we have a document store like Dynamo, we'll get the consistent hashing and handling of replication by default built into the database. So that becomes one advantage for us. And the user preference DB has to be like, it can also be a document storage, but it's better if we have a key value store, which sort of serves this request faster. So the user preference DB, what I'm thinking of is, uh, let's call it the user preference DB. I'm thinking of a key value store where I can host it on, we can have a Redis like store for that. But in fact, the data is not large, so we can use multiple machines. So actually what we can do is like we can use a store like, since we have to serve the data quite fast for this particular case, right? So my strategy would be if we have this database, like compute the data and push the data to user preference DB. So the base user preference DB can be another document store. And then from this document store, we'll have some application layer because the data set is not that huge. So we'll have some application data here, uh, which will load the data to an in-memory database. So let's actually have a in-memory DB. So this will be sort of like an in-memory small database, but that will be contained within an application. So if we have like an application within that, we can have multiple copies of that like that, and the entire thing we can move. Yeah. So basically the idea is like we'll have a lot of applications together, and each of the applications will have their in-memory storage. And what they will do is this data will be replicated, but there will be an in-memory cache. So we can store like a lot of so in-memory cache is like, and we can't directly. What I don't want is directly have access in request to this DB. The incoming request should be coming from the servers to these applications. These, what should I call it? Let's call them um, the actually this is the post service that the application is running. So this application, let's call this uh, user preference service. Yeah, user preference service. And the user preference service will have its own internal in-memory cache. And based on the hot user's request, whatever preference we have loaded will keep serving from there. And whenever we have a refresh, the user preference DB will basically load that. So we can, I mean, now we come to a different problem. I think the cache invalidation problem will come to that. And the cache invalidation problem, we want to have like a pull kind of mechanism from this. So each of the caches, they can start pulling from this user preference DB, and each of the application instances can start pulling from here and start invalidating the cache store. The intention here will only go to the DB and fetch the request if we have the uh, if we have the data coming from some new user. For existing user or hot users or frequent users, we should be serving from the user preference service. And if we can scale it up, like we can pin up multiple user preference services, we can actually redistribute the load, and a lot of the volume will start reducing, um, will stop reduce, will stop reduce to come here. Okay, so now I think the other part that we can think of is um, the cache strategies. So let's call it. So yeah, I think in terms of the DB replication part, the transaction DB and the user preference DB. So initially I was thinking of having a key value store. But instead, I'm thinking of I can have in-memory Redis instances for each of the applications where we will have the cache. But the user preference DB will be a document store, similar to Dynamo. And in this document store, the replication and sharding strategy will be very similar. But now I think the key part will be like just briefly how the key will be like we'll have a user ID, and then we will update the user ID to be the final list of values. The final list of values will be it's a JSON structure, so we'll have a one cat ID, and within the cat ID we'll have multiple products. Under. So this will be my structure for document store here. And now coming back to the ranking job. So how the ranking job will actually work. So this so we had just a brief explanation of the ranking job initially. So what the ranking job will do, it will periodically keep fetching from the transaction DB. Like as we have more and more transactions processed, we'll keep updating our understanding of a given user or the overall understanding of the product. And that understanding we will reflect in our user preference DB. So this ranking job will be an asynchronous job. And now I think the idea comes like how the ranking job will be triggered. Will it be periodical, or will it like how the data will be stored, how the data will be processed, what are the services that will be uh, doing it, and let's actually uh, do a little bit breakdown of this ranking job here, like how this ranking is. So this ranking job, since it's a offline and we can think of a batch processing or a streaming kind of job, let's try to dig deep a little bit into that, like how we can design such a service like that. So ideally, the input to our algorithms is like individually what the algorithms is run will run is that is still out of scope for us. So we will not try to go into the algorithm of it, like how the we'll do that, but it's mostly the data modeling on how the ingestion will happen. So what we want to have here in terms of the transaction DB, uh, we want to even scale the ranking job so that it doesn't clog too much because the amount of transactions will be huge. So we have to keep processing them. But as we have understood, like that the processing is limited by the user and product ID. The way we are sharding it and the way we are putting it into each of the shards for it, it will basically the user and product ID will shard into that. What we can have here is kind of a queue mechanism, like a Kafka kind of fetch streams we can have. So let me see if we have some kind of data here, which sort of shows that structure. I don't. So let me try to replicate that here. Some background like this, and just copy over. So what this queue basically means is in between we can have more here. So what this queue basically means is we will partition the data based on per user. So we want to partition data for a given user, put it into a partition and keep on appending to it. So I think here the idea matters is again one kind of distribution we have to do like for a given user, or actually let's imagine if we can do that. Um, So the idea is like we will partition into different queue for a given user so that when the ranking service job runs for a given user, it will update the user preference DB for that user, and that is basically separated for all the other users. But the problem that can happen is for any hot user or whichever is being serviced a lot, that will basically uh, degrade the performance a lot there. So what we can do it here is since we have the user ID and the product ID, uh, and then we have the user ID and category ID feature also there. If we split it up based on the user ID and category ID, then some, and actually since it's a transaction service, I guess like some user can make a lot of purchases, but it's unlikely. But still, we can do some kind of composite mapping and then hash it to multiple options. So each of the hashes here from the transaction DB to this queue, like pushing the data, taking the data from the transaction DB to the queue. So there will be one service which will be required to run here. So this service, let's call this, what should I call it? Service? Let's call this uh, algo NQ service. I mean, just because I'm out of good naming scheme. QQE, and let's also increase this one. Yeah, so we have an algo NQ service. So what this algo NQ service will do will it'll fetch the data from here from the transaction DB, and it'll also put the data into those queues. So it'll push the data into one particular section of a queue and one particular queue for a given user ID, category ID, uh, product ID pair. Should I do it by user ID, category ID, product ID pair, or let's actually do it by user ID itself? So we'll do it by one user ID. And what it will happen is we'll try to redistribute the load as much as possible. And actually, we can do that. So for example, if say one user is occupying 90% of transaction places, so that user will be split up into multiple queues. So what the final algo will basically do is each time an information is coming, it will be sort of like an append structure. It will pick up. So this algo TQ service, or actually there is no requirement of algo TQ service, or it can be thought of like inbuilt within the queue where I can directly push to that. But uh, but what we are having here is this transaction DB. We can have like a, yeah, it can be a change page. So whenever a new data is added to it, trigger a new request to insert the data to the queue. And whenever we have data available in the queue, this service will pull the data, and from this particular place, ranking service will pull the data from this particular queue and compute the ranking information um, and push it to the user preference DB. So how would the ranking service know what is the relevant, what is the current ranking information? So for that, it needs to, it the copy of that here. So the ranking service can push it to the user preference DB, um, but the user preference DB is not that huge. So what we can do is in the user preference DB, we can separate it out its read and write replicas because it will become sort of like read heavy. So we can have, let's say, three read replicas, and I'm assuming a very simplifying model here. So we'll have uh, two write replicas, and these write replicas will propagate the data to the read replicas. All is read replica. This read replica will have. So what the ranking service will write to is to the write replicas, and it can also read from the read replicas. Like it can also read replicas for. It will need to run for this information, right? So it will need to know for a given user what is the data that's there. So that will be just part of another. It will not be that huge. It will be very infrequent, and we can have dedicated read replicas just for that, which will be only used to serve for that purpose. So let's actually name this read replicas or color this read replicas into a different form of green, so we can identify and form of green. So this read replica So the ranking service will write to the write replicas, and it will read from the read replicas, and it will read from one dedicated read replicas. And these write replicas, what they'll do is they'll propagate the changes to other read replicas. And there are multiple ways that they can do this changes. So they can do, typically the databases, they do it by uh, the log shipping mechanism. So they have the transaction log, and they'll be shipping that log to the other write replicas. And just to ensure the stability of the database, like, or the reliability of the database, we can ensure the number of read and write replicas to be, if we have, say, six read replicas, and let's say if we have the total number of replicas as seven, we'll have four read replicas. And it's good to have odd number of ends here. So we'll have, say, let's say three ends here, and we can put it this way. Yeah, I'm just it's not required to do that, but yeah, something like that. So we have like three write replicas and four read replicas, so that are, because it's a read heavy system, so we want to make sure that we scale out the read accordingly. But we can have more read replicas, and typically if we have r plus w is greater than n, then we have a quorum of this distributed database, and which can keep on serving the request as well as the ranking service keep on updating them in the backend. That's, I think, our design part of it. And we have also discussed the caching section. So I guess I'll just briefly touch upon the caching behavior here. So what we need to ideally have is, we write down here, is cache invalidation part. So the caching will store only the hot user data. So the cache will have top users data, and my caching strategy would be based on TTL, because what matters in this particular case is the lightness of the data. So TTL will uh, be used for cache invalidation. I mean, based on the time to live of particular entry. And whenever, so the periodic batch of a kind of a daemon service will be running in the back end, which will combine all the entries which have expired their TTLs, and they will refresh it. And then it will be replaced by the least recently used users, will be replaced by that, or least recently. So yeah, I think that's all I have in terms of the design today. Thank you for joining in. See you in the next session. Goodbye.